Ruobin is a new faculty member at the statistics department starting this year, and she's working on things involving dempster-shafer theory and statistics, and that's what she's going to talk about today.
Thank you very much, Harry, for inviting me. This is a great pleasure. I've known this seminar series for a long time and always wanted to be part of it, and today is my chance. What I'm going to talk to you today is modeling uncertainty with sets of probabilities, and essentially this is large chunks taken out of the dissertation that I just finished this past May. And I would like to begin by motivating what this really is. So I guess I'm a statistician, and statisticians are very used to the idea that uncertainty can be modeled with probability, and probability becomes essentially the vocabulary for all of statistical inference and models and so on. But there's a lot more different kinds of uncertainty that could not be capitulated by just a single probability function, which is why I have over here there's more to uncertainty than probabilities. And I can give you examples of how this kind of uncertainty other than probability might arise in statistical applications, in data and the prior, if we're thinking about a Bayesian model, or even just the model structure itself, whether or not you're a Bayesian or a frequentist or otherwise. Hello, Glenn. Glad you made it.
Sorry.
No, that's okay. So, as I was saying, let me give you some examples about what I mean by uncertainty other than probabilities. So if you think about the literature on missing course data, when we go and, for example, administer a survey, it's very likely that you won't be able to get 100% people to respond exactly, precisely the way you intend them to. So usually you will get, maybe some of the responses that are missing or coarser than you might expect. If I were to ask you how old you are, you won't tell me, how many years, how many months, how many days precisely. You'll give me maybe a range, say I'm between 30 and 40 years or something like that. So the response that you get is essentially a subset of the state space that you intend to know. So it's of a lower resolution, so to speak, heuristically, of the kind of information that you ideally would like to have. And in order to analyze these missing on course data, usually the most prevalent approach would be to assume some kind of a missing data mechanism or course data mechanism, which is essentially a guess of how the data became such a missing pattern that you see. But this is usually something that cannot be refuted or substantiated with the data you have at hand. It's usually just a guess. It stays a guess. But really, essentially, what is going on is that we would like to not, preferably in the ideal setting, we would not want to make such unsubstantiable assumptions about the data we have at hand, which could, in fact, lead to erroneous analyses, such as with polls for elections and stuff like that. In Bayesian modeling, there has been this long, I guess a lot of people, if they have any beef with Bayesian statistics, it would be that it's very hard and very subjective to put down a prior. And in fact, a lot of times people don't have a precise prior or don't know what is the ideal prior. There are people who like to study, reference priors, objective priors, but these are all efforts that are aiming at somehow finding a rule or a procedure that could backwork the kind of subjective, what ought to be subjective belief, which is still, very arbitrary. But in fact, what happens is that if you don't have one particular prior, you could have a neighbor or a set of priors. Or even, in the worst case, you would have all possible priors. That would be the set of all probability distributions, and would like to work with that. Usually what we call non-informative prior, which is a uniform distribution over the state space, that's not uninformative at all, because to say that one element is just as likely as the other, that is a very precise piece of information. What we ideally want to use to express ignorance is to say that I have no idea what is the probability for this element versus the other. So that invokes not just one, but many probabilities, and those are the kind of uncertainty that we really would like to express faithfully. And once you're happy with the idea of using sets of probabilities to express uncertainty, you can do a whole bunch of things, which includes relaxing the model structure that you're working with. And this has come up in many applications in robust statistics. This dates back a long time. Peter Huber and Strassen, these are a collaborator who worked out what's called the Neyman-Pearson lemma to tell apart, which is just as you would with the Neyman-Pearson for hypothesis testing that we ordinarily know. But this is for if we have two sets of convex and closed sets of probabilities, how do we establish the most powerful test to discern against them? In econometrics, people work with these models who do not even have a single precise solution. Sometimes the model structure is written out so that they're inherently by design will just have a bunch of solutions, all of them equally likely, and you cannot equally likely in the sense that they are included in the set, but there's no way to further discern which one is more correct than the other. These are called the partially identified or incomplete models, and they are often seen in econometrics. Now, there is a large, at least a recent push into using so-called underdetermined structural equation to model what we see as a statistical phenomena. And this is, fiducial inference and Dempster-shafer theory are, in fact, this is the sort of the background that I came from, and this is kind of what I will be showing you as an example, a prime example of what is called the model uncertainty model structure today. And also, privacy and data confidentiality is a natural area where this idea of sets of probabilities naturally arise. In that, if we would like to say protect the individual's identity living in the entire data set, what's the popular proposal by Cynthia Dork and her colleagues is the notion of differential privacy. That is to say that for me as an individual data point, as well as all of the data points that are around me by 1 degree of distance, Hemming distance, the probability measure that's assigned onto some characteristic of me as well as my neighbor, they are not different by some kind of epsilon delta neighborhood apart. So that is to say, if I were to get to this neighborhood, there is no further way to discern where in this neighborhood that I lie. And in fact, this invokes a natural kind of structure of sets of probabilities, which I will not go into, but this is kind of the area that I'm looking into right now to find for the application of these sets of probability ideas.
Just ask where you draw the line between probability and uncertainty.
I'm using the word uncertainty to mean a lot of things. Probability gives the kind of uncertainty that we know what we mean by that. And there are also things...
I know what probability is,
yeah.
I don't know what you mean by it.
Uncertain, let's say, it would be different for me to, like, what's your guess on the 100th digit of pi? Versus what's your guess of the likelihood of raining tomorrow? Those are the two kinds of different uncertainties. But when we express our belief or probability for those two things, I think we mean differently when we are using probability to say those things. One is, in fact, a fact. It's just that we don't know, the 100th digit of pi, we just don't know what it is. But ideally, we should be able to find out, and that's a 0, 1 thing that is not debatable. But we can still talk about, maybe I think it's 50% this and 40% of that. Whereas for the prediction of rain, it's a different matter because, if we believe that we live in a 3-dimensional world and time is not reversible, then it's true that we, or at least nobody today would know about tomorrow. So there are, and also further things including, risk aversion. That will be another kind of uncertainty that is just in addition to probability because human beings kind of act in a way that seems to not obey by the axioms of Savage, decision theory and so on. So it's really meta-Bayesian in some way. So these I kind of all, call uncertainty, but really what I wanted to say is that there are a lot more than just what we are familiar with as probability, as the vocabulary that statisticians are used to express, in the model and for inference and so on. But in fact, I think when these so-called uncertainty are invoked as sets of probabilities for all of these applications, then they probably mean different things too. But just that, it's a richer structure and potentially give you another dimension to express different kinds of meaning when you have more than just one probability. Does that make sense? So let me define for you what is a set of probability. It's really simple. When you have more than one probability and you consider that a collection, that's a set of probability. Some are nicer to work with than others, but ideally, whenever you're thinking about more than just one single probability distribution, that's a set of probability. And usually we use what's called a lower and upper probability function to describe that set of probability. And those are really defined very simply that for every set let's just take the inf over that set of probability and the sup over that set of probability, and those give you two set of probability functions. And in fact, those can be figured out through one another. So really, you just need one, but it's easier to have, you know, the notation for both of them. And this is kind of a taxonomy of what we're kind of looking at. You have probability over there and sets of probability over there. As I said, not all sets of probabilities are nice to work with. There are ones, for example, belief function, which is a primary sort of object that I will be dealing with for modeling and so on. That behaves particularly nice, and I'll tell you what nice means. And there are also, these are just as nice probabilities, and they are really just, you know, nested concepts in a rigorous way of one another. Belief functions are called Shokei capacity of order infinity, and the lower the order, the more general the class gets, until you get convex and closed sets of probabilities. And all convex and closed sets of probability have this very particular feature that they can in fact be characterized by that lower and upper probability function, or just the lower probability function. In that if I can document that function, I know faithfully what is that set of probability function, and vice versa. They could sort of reproduce one another. If you have a weird non-convex or open set of probabilities, by taking the inf, you may not be able to work back the set of probability on its own. But once you have the convex and closed topology, then yes, it would be sort of a bijection. So we're only thinking about these kind of sets of probabilities for now. But you know, they have their limitations. For example, you cannot express the notion of independence with convex and closed sets of probabilities. They actually form some kind of a saddle shape, but we'll not get into those things. But kind of these are also, they're already very powerful in expressing a lot of things, and belief function being a special case of that. So we're going to stick with this for now. So there are two things I want to tell you about today. One is that sets of probabilities can actually do wonders. And I would like to discuss with you this model that in fact does prior free inference for multinomial data. That is using the Dempster-shafer theory of belief function. The belief function is what we will use to express in the posterior our inference for things. So prior free inference for Bayesian, that's usually, we would always say that's the holy grail of inference, right? You don't start with nothing, but you end up with something. That sounds like ideal. So in some sense, it is true that belief function, Dempster-shafer theory, would be able to deliver you such a thing, but there is a caveat in kind of the prior. So first of all, the prior will be truly free. We will be starting with an ignorant prior, saying that let's start with the prior of all possible probability distributions over the parameter space. So that part is true, but perhaps the trick lies in that as we go on and update the prior probability onto moving closer to the posterior, the Dempster-shafer theory would require the employment of what's called the Dempster Rule of combination. And that rule, having thought about it for a long time, I decided that the rule itself encodes some information. And this is what makes the second part of the talk, which is that in order to do conditioning with sets of probabilities, it's no longer a trivial thing. And there are rules, not just one, but many that we could potentially choose from. And depending on your sort of guiding principle, it's not clear which one is really the right one. If you go with the Bayesian decision theory of coherence, you might go with one. If you go with trying to sharpen your inference and get more precise answers given the data, you might go with the other. And they will get you into all kinds of weird situations. There are, in fact, three paradoxes that you have to engage in one way or the other. This is essentially what I'm going to talk about for the second part of the talk. So why, like, how this works and how this might not work, essentially, a positive side and negative side of cautionary tale at the same time. Okay, so but before that, let me just give you an example, or sort of a very concrete thing, a mental model for what a belief function is, so that we can work with this kind of thing. So belief functions are particularly nice because not only is it a lower probability, essentially, you know, it's tracing the lower bound of a set of probabilities. It's also, at the same time, a precise probability distribution, not on points, but on subsets of the state space. So one example that I would like to give you is this with a survey response that concerns 4 data points. Suppose I would like to ask you, in a survey, just 2 questions, in each of which is binary. I'm a skier, which is why this example was set up to have a skiing in them. So the first one, did you injure yourself in the snow last season? And the second one is, are you a skier or a snowboarder? I'm a skier myself. I think that snowboarders are usually more dangerous on the slope, which is why I might be interested in knowing the relationship between the injury rate and the type of snow sports that I play. So ideally, if I were to give this to everyone to fill out, then you would answer one way or the other, right? So suppose I'm giving it to everybody that's on the slope already, not somebody who don't ski nor snowboard. Then ideally you would like to get a sample space that consists of 4 points, 2 by 2, and the answer should be taking exactly 1 out of the 4 elements. But usually, if people were to leave out one or both of the questions blank, what you end up observing are not just these precise answers, but also those that are coarsened, in that one of the answers would be taking 2 values. So essentially, if somebody were to leave out the first question, they would essentially give you an answer that takes up 2 points out of 4 in the state space, and so on. And for somebody who left out the entire questionnaire, it would just be that you don't know exactly where on the one of the 4 elements that this person falls, except that it must fall in somewhere in that 4 elements. So if you were to tabulate everybody's answer, you get this whole distribution over subsets of the 4 element space. And all of these are made up numbers, but they add up to 1, as if this is a distribution over the subsets of state space. And the way that it works is that, let's say that I want to calculate the injury rate within the sample. I don't know what's that exactly, because some people didn't tell me if they injured themselves or not. But I could go and calculate at least at the minimum who injured themselves, which would be the fraction of people who answered specifically yes to the first question. And in this case, will that just be those 3 elements, and that will come out to be 0.3. And that's the lower probability for an injury. And the similar things go with the upper probability. I would just be taking everybody who said yes, as well as everybody who were ambiguous with that question. That would be the upper probability, and in this case it comes out to be 0.64. And in this case, because the lower and upper probabilities were derived from what seems to be a sample distribution over the subsets of the state space, they're in fact a belief function for the lower probability and a plausibility function for the upper probability, and they're conjugate just as they should be, in this way, that the upper probability of an event is 1 minus the lower probability of its complement. And that's what belief function is. And the reason why it's nice is because not only is it a lower probability function, but also that encodes a precise probability distribution, but on subsets of the state space. So the example that I'd like to show you concerns statistical inference, and it concerns how do we make inference about the multinomial propulsion vector without having to specify a prior. And the way that we like to think about it is this. Multinomial could be in some way described as a partially identified Poisson distribution. And we usually, the idea is that suppose that if all of the counts for each of the bins were not multinomial, but in fact some kind of Poisson process that went on for a little while, so its parameter is really lambda I times t. Now, lambda is actually non-identifiable as a model, because lambda is alias with t. When you want to make inference about, you can only make inference about lambda I times t, the product, but not individually, because it's just like linear model being not able to identify. But a margin of these lambdas could be identified, which is the normalized version. If I were to take out the entire norm of the lambda vector, then I can again be able to make inference about the relative frequency of the lambdas, as opposed to the other ones, because the t also goes onto the denominator. I essentially took it out by normalizing. So let's make inference thinking all of the x's are in fact Poisson processes, coming from having observed the process for a certain time, but not worry about the absolute the norm of the overall lambda vector. so that we will just make inference about Q, which is a normalized version of lambdas that is kind of mimicking what it is to make inference about a multinomial Q vector, which is the relative frequency across the K different categories.
So what is this norm?
Oh, just the sum. Yeah. So this is what we would propose for the model. The model state space, there are two things in there. One is the X vector, that's the observed data in K categories, the counts. And there is also the lambdas, which are the, we imagine these to be the intensity vectors for the X's. And we will observe the X's. Now, we will invoke what's called the gamma-Poisson count time duality to posit a sampling model for the X. And the way this works is this. So if you recall, what you learned in stochastic processes is that there is a count time duality between gammas and Poissons. In that, if I were to let a Poisson process go, if this is time, suppose this is lambda, right? In order for a Poisson random variable to take a value of, say, x, what happens is that let's just wait for exponential random variables to arrive individually, and there's one, and there's one, then there's one, there's one, and there is another one. So assuming that these are the arrival times of individual exponentials, and that's lambda, this Poisson took a value of 5 because there were exactly 5 of the individual exponentials that came before the lambda, and the next one came after that. So that we know if I were to denote these as, in fact, this is the sum of a bunch of EJs, j from 1 to 5, 5 being the x's. Actually, I should just read. This is x, and this is another kind of a delta E. And it would be the same to say that 5 of the exponentials happened before lambda, or that the lambda happened in between two adjacent gamma distributions that are different by an independent exponential. So let's use this characterization to say that, in fact,
is the word ancillary on your slide in some technical meaning?
Ancillary in the sense that this is independent of lambda. It's independent of all of the. So they're just, so what happens is that let's imagine that I have this completely independent pseudo-random number generator that would generate these EIJs, which are just independent exponentials with rate 1. And the x really is just whatever the number of independent exponentials that happened before the lambda. And that's essentially what this equation means. And EIJ, these are completely independent in that they carry no information whatsoever about anything, because we can generate them just on our computers and perfectly. And we make no prior assumptions on the lambda. So now here is what's getting a little bit controversial, because what's happening next essentially is a fiducial argument. Usually you would like to think that some things are random, some things are fixed, and maybe lambda is fixed and x is random and so on. But let's not think that way. Let's just say, given that we have these objects, we have some ancillary random variables, those are the e's, my x, which is observed, and my lambda, which is a fixed and unknown thing that we wish to know. Then what I said previously in this slide translate into this. That is to say that lambda essentially, so if you forget about, this is really just the product. But for each lambda I, it belongs to this GI, which is just the sum of the previous x numbers of exponentials. And this GI plus the delta EI would be the sum of this plus that independent exponential. So the lambda, each individual lambda really lives in this closed interval that is bookended by two adjacent gammas. And these two adjacent gammas, I have assumed that these are completely ancillary to everything. They are independent from the data, the lambdas, and everything. So this gives me a random description of what I think the location of lambda lies. That is in this random interval of GI and GI plus delta EI. And I do this for all of the individual dimensions of lambda I, and this gives me a k-dimensional hyperrectangle. And this k-dimensional vector of lambda lives in this random hyperrectangle. This is what the model about lambda is. Now, as we said, because we don't really know what lambda, because the lambda is aliased with a t in there, so we would like to make inference about the normalized version of lambda. Let's flatten this so-called random box or hyperrectangle into an object that is of k minus 1 dimension that's living in the k simplex. So that is equivalent of saying the normalized version of lambda lives in a simplex that is represented by their norms being this hyperrectangle. And I'll show you, so this q of x, which I denoted, where the x is indicating the dependence on x, because x decides what g is. G is implicitly dependent on x. This is a random polytope, or essentially a random polytope that's living in a k simplex of k minus 1 dimensions. In 3 dimensions, this is one realization of q of x, which, if I were to, so this is an example that's taken, if I were to, say, have a multinomial count of 3 dimensions, the first one is 2, the second one is 1, and the third one is 1. How do I make, inference about the propulsion vector that may have generated this data? That would be that I have a q of x, now q2, 1, 1. That would be randomly taking shapes of this type that's living in this simplex 3. And notice that if we were to do Bayesian inference, right, for a 3-dimensional multinomial propulsion, then what we end up having is going to be some kind of distribution over the 3 simplex, right? That, and if I were to draw samples from it, these will be a whole bunch of points that are perhaps more concentrated somewhere and more disparate somewhere else. Now, instead of having that, we have random sets instead of random points. If I were to draw this repeatedly, I will have this shape taking random forms here and there, but they will cover some areas more than the others, and then will move around, just like we would with the random points. But now they are very much like, the non-response course surveys. They are taking values as sets instead of points. So it's actually very simple. And remember that we did not start with having assumptions on the lambda. It was only through the essentially the sampling mechanism of the x's. So let me tell you a little bit more about q of x. It really is a fascinating object, and it's very easy to compute, and which is why I like this idea, because in fact we could sample from it IID, because we know perfectly the distribution, the joint distribution of its vertices. We also know how to characterize each of the qx, the random polytope, by a system of side inequalities, and this is very good for telling apart whether the polytope is covering or not covering certain points, and this will in turn give us results on 1 and 2 sample tests and test statistics and so on. So you don't have, this is kind of a detail, but essentially what the q of x, if you remember the hexagonal shape, the vertices can be written out in tiers, and the tiers are in fact all Dirichlet distributions. They are dependent Dirichlet distributions, and the way they depend each other is because they may be generated by the same set of gammas and delta e's. But all of them are distributed in this very intricate way, such that they're all marginal Dirichlets, and they have a joint distribution that will always give a very nice and convex and closed set, taking the shape of a polygon. And this is exactly why we can draw from them precisely, because we can only just sample a whole bunch of gammas and delta e's and just plug them in, and that gives us the distribution of the vertices. And that was, so I want to show you, this is an example where the polygon is sitting very nicely in the interior of the simplex, because my data observed, none of them are zeros. In case some of the data were observed as zeros, if you think about the box, what happens is that if x takes a value of 0, that means none of the exponential events happened before the lambda, right? That's when x takes a value of 0. So the hyperbox that would encapsulate lambda actually is living on one of the sides that's close to the sort of a origin plane. So in that case, the projection of the hyperrectangle onto the k-simplex would also be living on one of the sides, so to be aligned with these. But that's okay. They still follow the same Dirichlet distribution, just that they're degenerate on one of the dimensions. So that's still fine, just that they have this more particular shape. So that's one way of characterizing the q-axis. The other way to do so is to talk about its sides. So instead of vertices, but the sides. You can, I don't know if you can see clearly, but there are these dotted lines that come out of the vertices of the simplex that form like clamps that give you the shape of these simplices. And these are essentially telling you the relationship of the lines. And by knowing where, so one set of clamps, two set of clamps, and three sets of clamps. These three sets of clamps together decide this hexagon precisely, right? So by telling you about all of the sets of clamps that give you the hexagon, it's also equivalent of telling you where exactly that Q of X is. And in fact, this shape is called a density. So every realization of the QX with the fixed set of clamps are called a density ratio class of probabilities on the space of discrete, K discrete space, that is. Yeah, so as I was saying, knowing about the sides and how to describe the polygon, the polytope in terms of sides is very helpful in telling us how to tell apart the QX from the other. If you think about, again, drawing the parallel with Bayesian inference, if we were to have the posterior draws as points over the simplex, and we like to test for, the probability of, or either giving a confidence interval, a prediction, what do you call the Bayesian intervals, or some kind of a characterizations of the posterior probabilities in a certain set, we would only just be calculating the fraction of points from our posterior sample that fall inside of a set versus falling outside of a set and so on. With these random draws of sets, they can either fall into an area, fall completely outside of an area, or straddle an area. So instead of having probabilities in the posterior of a particular set plus the probability of its complement set add up to 1, these posterior random sets will give you inference that essentially takes value in 3 categories. The probability of yes, meaning that the set's falling inside of a particular area. The probability of no, meaning that the sets fall completely outside of an area. And the probability of don't know, or probability of not sure. That is when the fraction of these sets would straddle a particular area. So it's no longer sort of a stochastic 2-valued logic, but stochastic 3-valued logic that these random sets would give you. And towards the 1 and 2 sample tests, using these posterior random sets, we first would like to know how to tell apart. If I were to have a polygon, how do I know if this one is not intersecting with the other? Because that's how I tell apart whether those overlap or not. And in fact, there is something that's very nice and very neat about this. Suppose the Q of X live in a K simplex that's of K dimensions. K could be large. We don't have to be looking in a K dimension to see whether the polygons intersect or not. There is a one if and only if condition. That is, for all of its 2-dimensional projections, and there are K choose 2 of them. Suppose I'm projecting Q onto the ith and qth dimension, the 2 dimensions, which becomes an interval. So for all of the K choose 2 numbers of 2 projections, as long as none of the projections have as long as all of the projections intersect, then these K-dimensional things would intercept. What I mean is this. So again, taking the example with the 3 dimensions. Suppose I drew 2 of these Q of X's. These 2's overlap. And the way they overlap is that for all of the projections onto the 2-dimensional sides, they overlap. And the 2-dimensional projections are just intervals. As long as in one of the dimensions, the projections are not overlapping, they're not overlapping. You can go back and check this. This is an if and only if condition. So we have to make sure that all of the K choose 2 numbers are sort of 2-dimensional projections overlap, and there are so this is essentially a quadratic numbers of checks that you need to do. But with that, you could be able to tell apart whether the 2 K-1 dimensions of polytopes intersect or not. And with this, we could express the posterior upper probabilities for 1 sample test and 2 sample tests. How do I test for the hypothesis that the propulsion vector that generated this data is equal to a particular value that I'd like to know, then the posterior probability, upper probability for that really is just the probability for intersection, where this probability is generated by the g's and the delta e's, which are just the gammas and exponentials. That would just be the probability of all of these sides being on the same side, as we have shown, because we have to know that for all of the sides, the two-dimensional projection, they would have to intersect. That's the equivalent of knowing that my Q lives inside of a polytope. And the same thing for the two sample. We just have to know that both of the sides are intersecting for the two polytopes to be intersecting. So these are the ways that you would calculate upper probability for a 1 and 2 sample tests. And if you like to use, instead of just the polytopes themselves, but some kind of summary test statistic, you can do that too. And it's even easier because usually with one-dimensional test statistics, we could simplify the question from a k-dimensional one to a one-dimensional one. And the way that you would calculate this test statistic is really simple. By calculating the test statistic over the set of Q of x's that they allow. And the interval, or possibly the set of test statistics that they take, the closure of it for measure theoretic purposes, become, again, a random set. And this randomness, again, comes from the fact that Q of x is random. And we can have a whole bunch of these sets of test statistics that are distributed in some way, and we will be able to tell apart the test statistics falling beyond and below, or not sure about a certain criteria. And I have this particular Hellinger statistic as an example to show you. Hellinger statistic is really a continuous function working on two sets of probabilities. And the way that you would be working out the Hellinger statistic random set from the Q of x is really just to take the min and max over 1 or 2 sets, depending on if you're doing 1 sample or 2 sample Hellinger statistics. That would just be taking the extreme values inside of sort of one random set of qx and another random set of qx, and the min and max, because it's continuous, so there's no gap in between. It's really a closed interval, randomly distributed. And this is through simulation how things are distributed under the H null. The simulation is for 5 dimensions, with one of the sample being 100 and the other one being 108. And we took the Q to be some kind of arbitrary vector, and the distribution over the lower end of the Hellinger statistic is over here, where the dotted line is really that's in fact the line with slope 1. So this is only 0.1, that's 1, so this is actually of slope 1. And these are telling you about the quantiles, where the 50% quantile of the lower end of the Hellinger statistic random interval is around here, and this is the 90%. And same here for the upper end of the Hellinger statistic random interval. They're over here. This is under the null. And under the alternative, both are a lot larger than they should be. And then the null, of course. Although things are interpreted in the same way. One thing that I should say is that with these sets valued objects, you will lose power for sure. That's a given, because we intentionally sort of leave out all of the information in the prior and stuff in order to have this bit of gap in between, which kills power, of course, terribly. And I don't know how to evaluate this really, but this is how we applied this to a study. This is a small analysis called sieve analysis that's aimed at targeting the evaluation of whether a simple vaccine is equally effective on different strains of viruses that are all causing the same disease. And the idea is that you would like for the vaccine, of course, to be equally effective across the strains. Otherwise, essentially, this is kind of a, if one of the strains is particularly susceptible, then the vaccine is as if there is no use for it, because that particular strain could dominate it and still be able to, infect people. So we had this done on a multinomial data of 4 dimensions, of sample size that's actually also 100 and 108. And this is what came out to be the distribution of the Hellinger statistic, where the red curve is for the lower end of the Hellinger, and then the upper end is for the upper end of the Hellinger statistic random interval. And I'm not sure how to interpret this quite, because we don't know what's the ground truth for this. But supposedly this is how you would go about and using this method to do inference, by making up a rule to decide, for example, how I would compare the lower end distribution or the upper end distribution to a reference. And this I have plotted here that is the 95% quantile from a chi-squared 3, which is something that you otherwise would use as the reference distribution if you were doing a frequentist or just a simple kind of sample-based test. But again, a lot of decision theory has to go into kind of deciding how to make use for this, other than making up rules that are kind of just off the cuff. So that was the example. And the one thing that I guess, again, as I said, one thing I particularly liked about that example is that usually with these belief function based models, if we want to do it the Dempster-shafer way, using the recipe that has the that tells you how to construct these models and sort of the sampling distributions and how do you make combination of the data, usually it comes out to be that there might be quite a lot of computation involved in specifically having to take intersections of random sets. But the ones that I showed just now did not have to do that, because it happened to be the case that we knew exactly what is the distribution of the endpoints of that random set that we're concerned with. So computationally, it's a huge advantage not having to worry about that. But in general, a lot of things can be done about thinking how we could bring back the technology that has been developed on sequential Monte Carlo and fancier ways of sampling other than or beyond just simple rejection sampling to make these computation for more arbitrary belief function models much faster and in fact feasible. This is something that's basically entirely blank. The reason being, belief function, Glenn knew, this came to be way before the Bayesian revolution, the MCMC revolution came about. And when that happened in the 90s, belief function wasn't something that people, it still isn't something today, as I surmise, that the statisticians pay attention to. So that entire period where Bayesian computation took off, all of the belief function things did not, that was a missed opportunity. So there's a lot of catch up to do. But then what I would like to say is, now that we know a lot more than what we used to in being able to do Bayesian computations of its posterior, this should come together if we could be able to sit down and look at what are the tools that are already out there developed by very smart people over the past 20, 30 years. So any questions about that one? We're moving on to, that was the sort of the nice things. Now we're kind of looking at more of a challenge. And this is something I think I have to apologize to Glenn and Harry, who have both seen this before, but I guess for those of you who haven't, it would be new. But this is kind of a midpoint.
Well, back up and ask. So you gave two two examples with very different meanings. One was you were looking at a imprecise frequency count.
Yeah.
And the other one was you were looking at a kind of really replacing a parametric model.
Right.
Really replacing a multinomial model with something more complicated. So those are two very different things.
Very different things.
You're calling them both belief functions, but the meanings were different.
Yes, belief function to me is really just what probability is. Belief function is. It's a mathematical object that you could use to express uncertainty, however defined.
So I guess for a philosophical audience, the point should be made that you were interpreting it philosophically in two different ways.
Oh, they are totally. Just as you would with frequency count and what's my belief about the distribution of the proportion vector. They carry just the same meaning as you would like, your favorite in the Bayesian context or in the frequentist context. This is nothing more than supplying more than just one answer to it. But the fact that it does supply more than one answer is giving a sense of what is inherently uncertain about the model itself, or the process through which I arrived at the answer. But it's not intended to say that belief function ought to be subjective or objective or whatsoever. It really is just a mathematical object, and you could do or attach meaning to it as you see fit, I think. And the reason why I had the survey non-response example as a motivating example was this: that's something that a lot of people would be it would be easiest to attach to know that we might have coarse data and coarse observations and coarse frequency counts in real life. And that's also the example that we'll use to illustrate what's going to happen with updating of information. But that is not to say that this is the frequency counts is the only area that belief function could make use. Depending on whether we're looking at data or the model or prior, it's that already is saying that we should be interpreting things perhaps slightly differently. And yeah, no, just to say that we invoke in sort of perhaps a higher level tool does not mean that we should be thinking about that philosophically either way. So I'd like to talk about sort of the trouble or the challenge that lies in updating a set of probabilities. When things are precise, we have, it's really, we could just use the Bayes rule to go from the prior to the posterior or from the marginal to the conditional, either way that you like to see this. There's no debate. That you don't even have to be a Bayesian to do Bayes rule. That's just conditional probability, right? This is all fine. But when P is imprecise, this becomes something that's maybe subject to debate. And what I would like to present to you today essentially is a contrast of 3 rules. There are more, but these are, they're all very well motivated through some kind of an angle, perhaps differently, and also the kind of paradoxes that they might engage themselves in. And the take-home message there is that it's really, I guess this is a problem that has not been resolved. Hello. All right. Have a question? I forgot where I was. That was very cute.
The door.
No, it's okay. Yeah, okay. So basically, let me show you what I mean by that. So going back to this injury example, we worked out just now, the lower and upper probability for injury, which either is you can consider as a marginal information or something that's in the prior, that is before we see the ski snowboarder data. What ought to be your belief, right? Either way you like to think of it. Now, I wanted to ask about the conditional probability of injury given that you're a skier or a snowboarder, one or the other. Then one obvious thing to do for calculating the lower and upper probability of the conditional of injury given skiing is very obvious. Take the regular definition of conditional probability and just take the infant soup of those ratios among the set of probabilities that this frequency distribution over subsets would imply. And this is indeed what is one very popular way of doing things, and I had the index by a very fancy B for Bayes. So this is called the generalized Bayes rule. That is, take the ratio and just infant soup over the set of probabilities that you're contemplating. Except that there's a problem. Because if I were to do this and calculate the lower and upper probability for this very sample, right, for this very empirical distribution, I find that the probability of injury given a skier, the interval is wider than that of the prior, which we calculated that was 0.3 to 0.64. We just worked that out. This is the posterior conditional probability interval using the generalized Bayes for skiing, and this is for snowboarding. So what happens is that because skiing and snowboarding are the only 2 possibilities, you realize that either way you condition on one of the two, which form a partition of the entire space, the lower and upper probability interval became wider than the previous one, which is kind of crazy because it seems as if you had lost information by conditioning, regardless, right? Because one of these ought to happen, the thing that you're conditioning on, but just by conditioning, either way you're going to get something that's wider than it used to be.
Those aren't the only two possibilities. You have four possibilities, right? You could observe.
But to say you can only be a skier or a snowboarder. So you're conditioning not, yes, you're right in that I had a 2x2 table, right? And so this is yes, no, and this is skier and snowboarder. I'm conditioning on either the entire row or the entire, over here. Right. So those two things partition the space. So I could have said that I'm conditioning on that you are K, yes, and K, no. For the
right, but you're not guaranteed to observe one of those two things, correct?
Oh, I'm assuming that everybody who would be skiing is skiing. So this is to assume that the 2x2 table is the actual state space. That we're not thinking about things outside of this space.
No, I guess what I'm also trying to wrestle with the paradox. But when you condition on something, you condition on observing something. You're making the assumption that everybody either skis or snowboards, but that's not really. What you actually need to do is think about what you could possibly be conditioning on, right? Somebody could ski, but you don't know they're skiing, right? Because they don't necessarily report that to you.
So there are two things I'd like to say about that. So assuming that this is kind of a motivating example from the survey, don't take it to be that, I'm assuming that everybody is skiing or snowboarding. This is just assuming that if I were to have a distribution over this set of 4, then all this is trying to say is that I did do a conditioning on the partition of the space. If you were willing to detach the meaning from the story a little bit. The other thing is that it is true that I also came to conclude that I think that the trouble with sets of probability conditioning is that it's no longer the case, or at least when we do conditioning, there are different possible meanings of what it means to condition. Just that with precise probabilities, these meanings collapse into the same one, so that condition on something with a precise probability, it doesn't matter whether you have observed or not. It became the same thing. But with sets of probability, it makes a difference whether you are only thinking about the possibility of that event happen versus whether that event actually happened. Because the fact that something happened may also alter the state space in which you're operating. And that will change the whole game.
So on this slide, you don't have the word paradox. Were you going to talk? Have you already explained? Have you expressed already the idea that this is paradoxical, or were you going to?
It's paradoxical in the sense that people will be shocked to learn that by conditioning on either one of the partition of a space, the interval will become wider.
But if they somehow this paradox. If you just consider that this is about a partial knowledge of frequencies, then it's perfectly
I agree with you.
That you could know about an overall injury rate more than you know about it in specific subpopulations.
I mean, paradoxes are for attentions. They're not meant for.
As long as it's just about frequencies, one might. If you're calling it paradoxical, it's because you've gone beyond just thinking about this as a pitch story about frequencies. Am I right? You said this conditioning has something to do with.
So yes. So okay. So one thing I like to say is, please. I motivate this example with a kind of a very frequency attached meaning. But if you would like to detach from that a little bit, just think about very arbitrary, going back to becoming a probabilist or something. I have a 4-state space. A 4-element state space where I have a belief function on top. And I like to sort of maybe back off from discussing whether that means anything, whether subjective or frequency-wise. If I have this mathematical object that's just 4 dots, and I have a belief function on top of it, and I like to conditioning one way or the other, this might upset some people. That it seems as if, again, dilation is one of the three paradoxes I wanted to show you, but I wanted to say that's, in fact, this isn't theoretically, this is okay, this is not even a paradox or something that should upset you. It just looks upsetting because people look at intervals and think that interval means some kind of a precision of knowledge, and the fact that you are losing that precision upsets people. It could be a very good thing, right? Some people say to me after I talk to them about this, say, this is fantastic, because one thing that Bayesian inference cannot do is that once it has conditioned something, it's only going to go shorter, more precise, and ever does after that. There's never a way to back off when, or correct a model or something. So this is, some people would consider dilation even a good thing, to be able to, having faced a dimension of knowledge that could challenge the model and make the model all of a sudden grow regardless, wider. Could be a very nice thing. So depending on how you say paradox is, again, there's never really a thing of paradox. It's always explainable in some way or the other. Just that it could be upsetting to some people. It's upsetting to a lot of people when this was first discovered.
There's a difference between just saying that this is just talking about what the frequencies are. And it's another thing if you're saying, well, I'm going to use these frequencies to talk about how much I believe or expect a particular person to be injured.
Mm-hmm, mm-hmm.
It's when if you translated it into believing a particular person is injured.
Well, knowing that I am a skier.
Giving you more information seems odd that you have vaguer probabilities. But if you just think about it as frequencies and don't try to give any belief interpretation to it, then it's seems to be not paradoxical at all. Is that fair?
Yeah, I think so. So suppose that, because I am a skier and I don't ever foresee myself to become a snowboarder, I could be puzzled by knowing that if I were to learn that I am a skier, I would be predicting that this is the chance of my own injury, whereas not knowing that I'm a skier, this is the chance that you would supply. Or if the doctor were to prescribe, or diagnose you with a certain disease, then knowing about your exam or physical exam, the diagnosis is going to be less precise. Seems to be paradoxical that way, maybe.
So it only becomes paradoxical when you bring in this idea that this conditioning is telling you how more information would change beliefs about a particular individual. But then you can make similar paradox. I mean, and then picking up now on what Harry said, that, well, there should be, if you're talking about how more information is going to change beliefs, you need a model about why you were told that information. And without that model, even purely, we know these, I'm sure you're familiar with the paradoxes where you have additive probabilities, complete probability distributions, and still because you don't have a model for why people are giving you information, you also have paradoxes.
Yep. No, I agree with you. I think so.
In that sense, I don't see this as peculiar to the imprecise story. The lack of a model for new information, to me, is what's driving the paradoxical sense here, and that applies equally to the case where you have precise probabilities.
In precise probabilities, unfortunately, none of these could happen because you don't have a interval to be working with. I think with precise probabilities, just a lot of the trouble of not being very specific about the becoming of the evidence does not actually affect the outcome. Because we're working in this very degenerate space that has just single probability. It doesn't have that richness to even reveal the logic.
But it changes probability. If you don't have a model for the information, it can change probabilities in paradoxical ways. So you get, well, we could talk, maybe you don't recall the kinds of paradoxes I'm talking about, but we could talk about it.
Yeah, I don't, but okay. Maybe that's good for dinner time. Anyway, this was upsetting when it was proposed, when it was discussed. That was 1993. Teddy and Larry Wasserman at Carnegie Mellon wrote this paper. And let me tell you, so this is exactly what's going on with dilation. The intuition behind dilation for at least this 2x2 kind of situation is that what happens, this has nothing to do with conditioning on sets of measure 0 or anything. We're just dealing with discrete space. Everything is positive. There's no sort of measure theoretic problems here. The problem is that the way that this belief function is specified on the set of 2x2 table, it's very confused about the relationship of the random variable yes and no versus the relationship of skiing, snowboarding. That is to say, the set of probabilities posited by the belief function encapsulates some probabilities that think those two events are positively correlated and some that think it's negatively correlated. So it actually intersects with the independence plane. And when you have that, the posterior would dilate. So that is a necessary condition for dilation. So, which is to say, if such kind of conditioning on a binary partition on a space happens, then it is necessary that the set of probabilities that's being contemplated would have an intersection with the independence plane. That is, it's confused about the direction in which the information are helping each other, which is exactly as you said, which is why knowing about this other dimension actually hurts the so-called knowledge of the other dimension. Because you have no idea. What the generalized Bayes rule does, if you look at whether this is trying to go for the extremes and try to protect itself. That is when you do the infinite soup over the whole set, you just might go wider in that way. So that's what we said. The generalized Bayes rule is the rule that I used for this case of dilation. And dilation, if I were to represent it in this graphic form, it just means that conditioning makes the interval wider regardless of which element of the partition that I was conditioning on. There are two more rules. The Dempster Rule, that's in fact the rule that I used for the multinomial inference just now. It's slightly different. If you look at the expression for the upper probability, it's no longer the soup of the ratio, but ratio of the soups for the upper. And then the lower you can work out by conjugacy. And the same thing with the geometric rule, but it goes first by defining the lower probability conditional as the ratio of the infs. Well, with the condition that the inf of B cannot be 0. If it's 0, it does not even answer the question. Yeah.
Can I just clarify something which I think you just said? That's good. It's there. But the generalized Bayes rule doesn't always dilate.
It doesn't always dilate. Yeah. It does sometimes. And these are three distinct rules. They are all the same when the set of probability actually is singleton, because there's no super inf to be talking about. But they are different as soon as this set of probabilities is no longer singleton. So this is a reverse kind of paradox to dilation, which is called contraction. That is, if you were to condition on a partition of events, regardless of which one that you're conditioning on, the posterior interval actually grew shorter than it was before. So this is also kind of weird, because this is as if saying that information just came out of nowhere. So by knowing anything, I seem to have a sharper interval somehow. This is also kind of, in the paradoxical, as much as you would think dilation is paradoxical. And the other, perhaps more grave paradox, and this is in fact a defect in sort of a Bayesian coherence point of view, is sure loss. That is, if you were to condition on either one of the elements in the partition, all of the posterior intervals are going to move completely to the one side of the prior interval without any intercept. So you have abandoned your prior position entirely and went one way. Not like, basically for all of the possibilities you might want to condition on. This is called sure loss. Sure loss in the sense that, if I knew that you were going to do this kind of updating, I could make a bet with you and make you lose money for sure, right? I would just have to bet this much, and you will definitely accept. But now I know the next time you're going to move over there in the posterior, so you would have to pay me for more than one. Pay me for like an epsilon amount of dollars, depending on the size of the width of that gap, right?
So that's something that I don't think is right, and I think that's what they said. But you don't know you're going to be able to condition on B or B.
But I know for sure that regardless of which one that you're conditioning on, you're going to move to one side.
No, you don't know I'm going to condition on either of those things.
Right, I know. Yes, but this is to say, assuming that I do, I guess.
Well, I think it matters because you're going to be making a bet that might either might have to be conditions on the bet. I guess it's a bet that would only take effect if one of these two things gets observed, or something like that. And in that case, is it clear that the person would still stick with their prior if they now knew that after the thing happens, they're going to be conditioning on?
Well, if they don't, that means they're not abiding by the rule. I'm just saying that if you were a robot that would work in this very strict and sort of way, and a robot is someone who buys the Bayesian idea that in order to say that the robot embodies an interval means that he's willing to, pay for at least the lower bound of much to get into a bet and buy the bet as to sell a bet for this much and buy a bet for this much. That's what an interval probably could mean in a decision theoretic way. And if the robot were to do that, and if I knew that the robot would have to condition on one of the two events, and then I know the robot would have to, because I can also work out, according to the rule that the robot is encoded with, that the robot is going to move its own belief onto one side, then I can just trick the robot into getting a bet with me and lose money for sure. That's a lot of assumptions, but this is to illustrate the behavior of the rule, giving perhaps slightly uneasy answers. But again, there are lots of things that's potentially wrong with having to do this kind of procedure with sets of probabilities. That is, all of this is saying, if we were to do the naive generalization of conditioning from what we think of that applies to precise probability into the world of imprecise probability, we get into these trouble. And this is, if anything, teaching us that we might have to think more about what, in addition to knowing just the events that we'd like to put behind a bar, what are the additional things that needs to be specified? For example, the process through which the evidence is generated and what it means to be conditioning on certain things and so on. But if we were to do the naive extrapolation, we get into these things. And just some results to tell you about perhaps this irreconcilability between having to choose between the rules and having to choose between the paradoxes. This is what we have. So the generalized Bayes rule cannot do neither contraction nor sure loss. Because if you think about those things, if anything, these are worse of a crime in the coherence sense. Because sure loss, obviously, we said that because you could be made into getting a sure loss bet. Of course, that's not okay. Contraction, that's kind of like that too. Because if I know that you were adopting a procedure that would contract for sure, I could somehow set up maybe some kind of epsilon amount of bet and make sure that it's small enough to be making off a little of the money from you. Because I know for sure that your posterior probability is going to shrink into what you have taken as the prior probability. So those two things would get people into essentially money trouble, and that's the worst kind of trouble in a Bayesian sense. So the generalized Bayes rule does not do that. Yeah.
With the generalized Bayes rule, this is the upper version, right? There's a lower.
Oh, the lower version is all of them give the same. So the lower version is 1 minus upper for the A complement. So they're always conjugate for all three of them.
Would the generalized Bayes rule, the lower version, would contract?
Oh no, the lower version would give you the lower bound, and then the upper version give you the upper bound. Then the entire interval decides if it's
about the interval.
Yeah, it's about the interval. Yeah. Right. And the second thing that we learned is that the generalized Bayes rule is the most conservative of all three, in that it always gives you a superset of probabilities compared to either the Dempster rule and geometric rule. That's why it dilates more. So a lemma to this is that it dilates more often. That is to say, if either one of these, Dempster rule or geometric rule dilates, you can expect the generalized Bayes definitely dilated. because it encompasses a superset of probabilities, but not the other way around. When generalized Bayes dilate, these two may or may not dilate. It's not clear. The third thing, which I think concerns inference more, is that, again, we said that one of the holy grails of statistical inference, as far as Efron is concerned, is to get posterior inference without having a prior. So if we really want to work with so-called vacuous priors, like we did with the multinomial case, neither the generalized Bayes rule nor the geometric rule will get you there, because generalized Bayes will just not sharpen at all. If you start with a vacuous thing, you will end up with a vacuous thing. That's why the sup and inf operation gives you. There's no way to get anything sharpened regardless of how much data you have observed. The same thing with geometric rule. It's just what it is. The Dempster rule is the only one that will give you something that is essentially something out of nothing. I don't know if that's a good thing or a bad thing. But that, again, is an illustration that there might be, there, of course, is a lot of information that got into the rule itself. And the fourth one is a very interesting thing. This is, again, because we just said that contraction and sure loss are kind of more problematic decision theoretically, because supposedly you could be getting into these incoherence troubles. But this theorem is essentially saying that dilation and contraction are not too far apart from each other, if you look at what the rules would do with them. So supposedly working with a binary partition, as we did with the snowboarding and skiing case. So if this binary partition, which is the sport type, dilates injury A, under the geometric rule, it would contract A under the Dempster rule. And if it would dilate A under the Dempster's rule, it would contract A under the geometric rule. So those two things definitely have, and not vice versa. So it's dilation that implies contraction with the other rule, but not contraction implying dilation the other way. I don't know how to interpret that, but at least this is bridging sort of the so-called gap where dilation previously is at least immune to decision theoretic, sort of criticisms, whereas these two are. But it seems that they are not as far as apart from each other as it seems, I guess. So that's it. That's all I can tell you about these things. I don't have an answer for them. I think working with sets of probability is just very difficult, and I am thinking along the lines that it's just that we have to think more carefully about what it means to put something behind a bar. There's a lot more that needs to be specified than just the events themselves, or the partition, or even the sigma algebra, or the I don't know.
I missed something here. Notation. If B dilates A under G rule.
G is the geometric rule.
Right, but what's B then?
D is the Dempster rule.
Oh, B is the set. Oh,
so yeah, sorry, it's terrible because I have so many of these sets and partitions and supersets. This B is the partition. A is that event. Yeah, yeah.
It's not the same thing.
The Gothic things are the rules.
Oh, you've got a distinction between Gothic and script here.
Yeah, this, yeah.
Just to clarify so does it mean for every partition, if one element dilates, the complement also dilates? Dilation
is for the entire partition. It's defined on the entire partition. So it has to be that every element in that partition makes the interval wider for that to be called a dilation. So with the sure loss, all of them has to be for every single element in the partition. Yeah. Otherwise, I won't even be concerned. It's just that some situations it's better, some worse. That's it, by the way. That's all I have. I have a plug. Oh, by the way, this is just to show you. This is the last slide. What happens with dilate? So for the ski case, we saw that the generalized Bayes would dilate. In that same situation, Dempster rule dilates also by a little bit, but as you can see, because it gives you a smaller set of probabilities, it's not as much as the generalized Bayes. And in this particular case, the geometric rule contracts. But I could also set up the numbers differently so that this one would dilate, this one would contract, where that one dilates also, and so on. But either way, these intervals are going definitely to be wider than the other ones. That's as expected. And this is a plug. I'm part of this Society of Imprecise Probability meetings now, and this is their slogan, which I stole for my first slide. There's more to uncertainty than probabilities. They're having a biennial meeting this July in Ghent, Belgium. We will be having a speaker from Ghent actually in a month of time, and I'm sure he will tell you more about what's going on, but this is certainly something very exciting. Okay, thank you very much.
So I have a general question about imprecise probabilities for you, maybe for Glenn too. So when you think about the case of ski and snowboarding, there's a very nice sense in which you can use interval value probabilities to model the uncertainties here, and the precise boundaries can be sharp. But there are cases in which the interval value probabilities might be too precise too. We have precise endpoints. So just wondering, what are the kind of current research projects on this to introduce more imprecise or fuzzy endpoints into machine learning here?
We talked about this over email. Glenn, do you have anything to, I'm curious about what you think about this too.
Well, I was never a fan of the word imprecise in these. You could talk about interval valued or you could talk about betting offers that don't form a probability distribution. I mean, the economists talk about incomplete markets. So the word incomplete is different from imprecise. So I don't want to put myself in a position of defending the word imprecise. I never bought into it.
I see.
I guess Peter Wally was the, I think, maybe he got it from somebody else, but he made it very popular. I was shocked to find that he has reemerged.
So you looked into the book?
You told me that.
I did. Do you look more into that book?
No, I don't know if I ordered it. I did see it on Amazon. But
Yeah. It's also very cheap when I got it. It was like $4. So Peter Wally is this.
Did it say anything more about where he is?
No. No.
I was totally unaware of. Does anybody else follow this? Why don't you tell what the world knows about Peter Wally?
I have no idea. I don't. So all I knew was it seemed. So this is the sort of anecdotal story from Teddy that when SIPTA first got started, which was back in, they're running their 20th thing, and then that's biennial. So that must have been many years ago when it first got started. Wally was on board an event. It was on board for a little bit, and then somehow he got into a very minute. He got into a big argument over something very minute, perhaps about the name of the society. And decided I cannot talk to any of you anymore. Goodbye, farewell, my friend, take care. And he took off. And just nobody knew where he was after that. But he was, he wrote this book on imprecise probability, which is, oh my God, it's very dense. And he of course, as Glenn and many people probably thought that he just disappeared, but 2015, he published a book called BI Statistical Inference. BI for bounded inference. He didn't even care to spell out BI on the cover. It was left as BI Statistical Inference. It's a yellow colored book.
He has abandoned the term imprecise too. Have you gotten the book?
I got the book, yes.
Does it have the word imprecise in it?
I don't know. No, I don't think so. I'm not sure, yeah. I'm not sure. It's bounded inference. At least that's what it's called now.
Well, he was a student of, I guess what I recall, I have seen one photograph of him. He was a student, I think he was from Australia or New Zealand, I think. And he was a student at Cornell, Terry Fines, who was a friend of mine. And Terry had written about what he thought was a frequentist. And I don't think Terry used the term imprecise probability. you may have done, but Terry was interested he was interested in what I had been doing in the 70s, but he was also in his own idea of a frequentist model for probability intervals, which was that you would actually have, some kind of a physical situation where on repeated trials there would be some instability within bounds, so you get probability, a purely frequentist understanding of probability bounds. And he had some students working on that, and then Terry came along, or rather, Peter Wally came along and was very brilliant, had his own take on this, and was more of a De Finetti orientation. So his idea was these are betting rates, and it's just that we're not willing to take either side of a bet. We're willing to bet on this side this far and this side this far. So there's like a bid-ask spread.
Right. Okay.
So basically, it was a bid-ask spread theory. And I corresponded with him in the 80s. He put some of mine in this big green book he wrote, which is out of print. There's I think there's a couple, some of our exchange of correspondence in there.
You are talking about his book, right? That's the very book, the chapter.
One.
Yeah.
Back in,
I remember because that book, if you can look it up on Amazon. It's on sale for like $1,000.
yeah, because it's out of print.
I was shocked the first time I didn't realize, and I came to you actually. I asked, what's going on with that book?
So he doesn't want to have it reprinted, probably. So he was, anyway, he was very eccentric and kind of fled from Cornell, I think, because it was too much teaching and he didn't have time to do research. So I think it's a little bit of a manic depressive thing going on or something. Then we knew that he had disappeared, and then I think he reappeared 20 years ago in '89, and then he disappeared again. And I'm sure I talked with Terry Fine, who had been his advisor, and every time I talked with Terry over the years, he bemoans Peter's disappearance as a real loss to science. And I'm sure that I would swear that my last conversation with him was since December 2015, when this book supposedly was published.
And there was no mention of the book.
Terry had not heard about it either.
Right.
So
Your last discussion with
Terry Fine, yeah. And so when Ruobin told me that he published this new book, and I could look it up, I was shocked.
Nobody knew.
You should have brought it with you.
I should have. I'll bring it next time.
I should have come to your office too.
Yeah.
So the title, Inquiry probably comes back to this person.
So the book, this group of people, the Asipta Society, yes, they founded that society being inspired by his work. It was a group of people that, like Teddy Seidenfeld and Dirk de Koeman, were interested in his work and thought it would be a framework for things they'd like to do. I might have been involved in like the second meeting or something, not the first one, I don't think. But so I only went to a few meetings over the years. But for a while, I think, I did go to a few of the meetings, and I felt it was kind of the most philosophically oriented foundations of probability group. It was kind of when I was younger, there were other groups that statisticians and philosophers would get together. And for a while, I think this organization played that role. I think perhaps, aside from a meeting or two, they were always in, except for Terry Fine at Cornell and Teddy Seidenfeld and his friends at Carnegie Mellon, they were all Europeans.
Yep.
I think to some degree this Bayesian fiducial frequentist meeting has taken up some of that space in the U.S. now.
I would hope that is the case. And Shali and I went to we had Teddy come to the fourth meeting, which was almost a year and a half ago now to Harvard, and he advertised for the SIPTA, which was 2 years ago, and Xiaoli and I went together with Jim Berger and Teddy. There were 4 of us coming from the States, whereas the rest are all Europeans, as you said. And I think the last time they had a meeting, SIPTA meeting in the States was 2002. That was in Pittsburgh, Carnegie Mellon.
Right.
And Art Dempster was actually the keynote speaker, although he doesn't, he vaguely recalls that he gave a talk there. And no, it's just been...
some dempster-shafer stuff.
There are people who do dempster-shafer there. There were a session dedicated to dempster-shafer, but from a very different point of view. It's not statistical inference at all. It's something else.
So I think it was kind of has been sort of a place where everybody was interested in foundational issues. That's their thing. It's not all Peter Wally stuff.
No, it's not. Yeah, that's right.
But I think that was kind of the core that held it together.
So I guess there is no way to make it really precise. In the sense that the boundaries even are not precise.
Well, there are people that you could answer this. You've been listening to them more often, but there were always some fuzzy people in this.
There were fuzzy, yeah.
So
there's some efforts to address your question, I'm sure. Did you hear anything of the plan?
You mean the fuzzy logic, the fuzzy sets?
To address Eddie's question about being truly imprecise but making the endpoints fuzzy. I mean, that's the funny thing. You could say the same thing about fuzzy. The fuzzy thing was always end up with numbers. So
Yeah, that's what I would say too.
I was looking into fuzzy sets, and I'm thinking that itself is too precise too, because you got this fuzziness indicator and function. You had a sharp cutoff between 1 and non-1.
Because, so the question I would ask, I think I agree exactly, because eventually if you were still living in the space of having to use probability to describe fuzziness or whatever, that reduces to probability. If you think about what random sets are, random set is a set where the endpoints are in fact random. So in some sense, that's the randomness in a set. But still, that translates into a precise sort of interval if you start, integrating over all the possibilities. So there's no getting around that. I don't know. I'd be curious to hear if I've only briefly looked at Susanna's paper.
Yeah.
I don't know if what was. I don't understand precisely what she meant by the sort of insurmountable
right. I think
undecidedness.
There's a point there in the sense that every time you want to have some mathematical model of imprecision, you run into shock points somewhere, some level
of course.
And I think that's a kind of curious feature of probability, but it's not serious for using probability itself. It's just kind of when you consider situations when you have chances that are defined on a kind of fuzzy boundaries, then there's no precise way to define the chances with probability or even fuzzy sets or probability functions. And that's where I'm kind of worried. But if there's no machinery yet, then maybe it's an open question.
I think the problem is that the question itself has not. I think if we know how to pose that question more precisely, we would know the answer. It's just, I get what you mean, because that's something that troubles me too, but just, it seems to me that every time we try to make a step further, kind of departing from the precision, then there is another layer of precision that I never get around to avoid.
Yeah, I can see that too.
So, anyway.
There is a very small group of people who are trying to model the value of probability functions are not real numbers, but sort of you think of the real lines as just patches of infinitesimal intervals. So you get it run with the precision by thinking of real line as what they call accumulations of sublocales, like point-free topology. So you don't have points on the real line, and then you do your
Donkey topology.
Sort of, you can think of it as donkey topology, and that way you sort of get to feel, it can never be precise because you are always working with intervals and you can't shrink intervals into a small point, into a point. In that way. So you basically change your notion of probability on that model.
That's kind of like surreal sometimes.
Exactly.
Yeah, I have to think more about that. I still think that is too precise in the sense that you still have difference between 1 and less than 1 probabilities. So you talk about the probability over the whole region, and is it less than 1? Is it 1?
We can talk about this later because there are actually, once we move into this quality, situation is a model. So it's not like when you choose, first you can't choose a point, but if you ask, for example, if you ask for a number whether or not it's bigger than 1 or smaller than 1, it's not a solution. It can be both bigger and smaller, or it can be smaller, even either smaller or bigger. But yeah, we can talk about this later.
So change of classical logic might help. Okay.
Well, I can go back to this point about vacuous prior. When you referred to vacuous prior, you're referring to more than a vacuous prior. You're referring to this way of taking of Mark Dempster's way of taking a Fisherian parametric model and kind of generating it from a single probability distribution, if I can put it that way. Your gamma,
Art's models are very much parallel to fiducial models, just that the prior part is lacking. So
well, but the prior part.
No, sorry. In parallel to fiducial models, it's not the prior part is lacking. It's that the structural equation that they put down is not invertible.
Right, but you replaced instead of starting with a parametric model, you started with a structural equation.
Yes.
That's right.
Yes.
So it's not just that you left out the prior, you've put something else in, the structural equation.
But the structural equation replaces what is, what's the sampling distribution supposed to do, as opposed to what the prior is supposed to do.
Okay, in other words, if you have a structural equation, you don't need a prior, you can put it that way. But it's not. Okay, but it's not just a vacuum. It's not a matter of merely making the prior vacuous. It's a matter of a different kind of model.
It's a different kind of model.
It's a structural equation instead of a class of probability distributions.
Yes, I think so. All of the randomness also comes from the ancillary.
The structural model means there's only one probability distribution, not a class of probability distributions. And that's the whole key.
Well, that is one probability. The one probability distribution is generated by the set of ancillary variables, and the inversion of the structural equation gives you the multi-value map, which gives you the belief function. But to say that it's prior free means that there is no specific distributional assumption on the margin of the lambdas, which are my parameters. That's all it means to say that it's prior free. But it's of course a catchy word, and as we know, if you start with nothing,
Yes.
Yeah.
My point is just that for an audience, yes. I'm not sure your audience here would know what's going on there. That you aren't just taking the Bayesian picture and leaving out the prior. You're adding another structure.
Right. The structural equation gives so the structural equation is more than the sampling distribution. Yeah. The same sampling distribution could correspond to multiple structural equations, and they may actually lead to different solutions in the fiducial sense.
So what is
sampling? Meaning that if I have a parametric model that
sampling distribution
for the model, I'm not saying that's the right one, but the one that you would like to use. Say for multinomial, x.
What does sampling distribution mean?
The sampling distribution meaning the x conditional on p or q is multinomial, and q. That's what I mean by sampling distribution.
So a sampling distribution is not a single probability distribution; it's a class of probability distribution.
Yes. Yeah.
And you're getting that whole class from a single probability distribution plus a structural equation is what is happening here.
That class is, I did not.
I'm insisting on it. I've already said it. I don't want to.
I think the structural equation itself does nothing. It's a deterministic equation that just links x with q and e, where e, I'm going to later on assume something. But the structural equation itself is deterministic, and I don't have to associate. That's what it is. I don't have to necessarily assume that there's a class of something having to imagine different values of q or different values of x or different values of e. But once I do, that becomes a lively thing that gives us the model. But that's, yeah.
So I'm wondering how this is ending up. How is, I guess in your skiing example, how is the model there different, is it different than just than modeling non-response as a response?
That is equivalent if you're willing to consider all possible coarsening mechanisms. So by coarsening mechanisms, I mean assuming that there was a true distribution that generated the data, and then there is a coarsening mechanism that says, given that my data is actually x, what is the possibility that it would take subsets that contain x? So this is a two-step process to specifying the coarsening mechanism. And if you were willing to consider all possible ones that are congruent with the observed data, then you do get the belief function. Another way to say this is that you are willing to consider the set of vacuous coarsening mechanisms that are congruent with the observed data. So you're not making assumptions about the fact that people are undecided voters. Were they actually Clinton voters versus Trump voters? There's no assumptions about that at all. Or that you have assumed that from 0 to 1 is all possible.
Right. So with that said, I still don't understand the issue with sure loss, because you're not conditioning on the third possibility, which is that somebody didn't respond. And that's different from saying that they must be a skier or a snowboarder.
Yeah.
It's that they didn't respond.
Yeah. So you're saying that there should be a consideration of conditioning on both of them, or something, a union of those two. That is, instead of every element of a partition, but also subsets of a partition. Subsets, yeah. Yeah. I don't disagree.
Has three possibilities, and you've conditioned on 2 of them. And so, if the bet had a third option, which was they won't respond, then I'm willing to guess that there wouldn't be a sure loss. But
I don't know about that. And again, this is to say that this is a.
In some sports, there's ties, and you can bet on win, loss, or tie, draw, and that's an outcome.
Mm-hmm.
And so,
yep.
This seems to me that I'm not sure, but I could be wrong. But it just seems like there's a. I know this isn't your observation either. The sure loss is something that's been around for a while, but just that. In probability, we think of observing precise outcomes, and we think of the set, a set of 2 things as meaning that you observe something in those 2 things.
Mm-hmm,
but this is not what you're actually saying. When you observe the set of 2 things, it's that you've observed somebody not saying either one, and it's actually a different. It should have different notation probably, but it's a third possibility.
Right. No, I think you're right. But again, I think we said that before. This is only the definition of dilation was adopted from Teddy and Larry's work, and the way that they did it was literally extracting what you would do with regular kind of conditioning on elements of a partition, and not thinking about conditioning on subsets of the partition. But if you do that, it could go on, I guess. So the one thing that I would say, though, with the binary set is that if you were to condition, in the specific case with the partition is binary, if you condition on the union of them, you don't condition on anything, right? That's just the prior. That's what the rules would give you, at least. That it's as if you didn't condition. But if you have a set of 3 things as a partition, that might be different.
Sort of a follow-up on Harry's question. I was wondering, this is more like a conceptual point. I was wondering whether or not you think of uncertainty. Well, at the beginning of the talk, you talked about uncertainty as capturing many things, including information, risk, and other things. In particular, I was wondering whether or not you think of uncertainty as something different from ignorance. So I think one thing that I got from Harry's remark is that sometimes you don't know because you don't have enough response. So sometimes you don't know, and sometimes you want to capture uncertainty, not that you don't know, but you know something, but you don't know how to specify it.
Okay, so yes, I agree. So what I would like to say is system probably is not going to solve all kinds of ignorance. It's only good when you know what, at least you know what's your state space. If you have no idea what the state space is, it's going to be a problem. You can do things like, putting a space holder thing there to denote whatever that's unknown, but that's kind of cheating in my sense, in my opinion. This only works if you have a fixed state space, but not knowing what's the distribution on that, then you can work with sets. But if that's not true, no, it won't. I mean, that's another kind of ignorance. Not knowing even what is, and in fact, I think that's the real challenge of, in reality, we don't even know what might be the possible outcomes. And in many ways, that's even worse because I don't even know where to start with a problem like that. This does not take care of that, I don't think.
Yeah, but
Looking at me.
Yeah, no, I'm curious to see what you have to say about that.
Can you repeat that?
So ignorance could take on many forms, right? Ignorance, I'm talking about, say, vacuous priors that I don't know what to put on my prior, but at least I know I have a lambda that lives in the real line. I have to put some kind of prior on that. I could at least invoke the set of all probability measure on the real line to denote my ignorance. But what if you don't even know what's the range of values that lambda could take, or something else? There are other, ignorance can be of many forms. I think sets of probabilities cannot solve that if you don't already know sort of the arena in which you should be.
It's all more relevant to frame of concern.
Yeah.
So you want to discourse on how I look at these things? This is I'm not big on sets of probabilities. To me, so we're talking, our seminar is Foundations of Probability. We're interested in probability, but I don't, it seems to me that mathematical probability is a very special kind of uncertainty. And I don't think that it applies to most uncertainty in the world. I'm fine with that. And I don't think that sets of probabilities are a very, I'm interested in the way I understood Dempster-shafer theory as taking a situation where you do have probabilities about something and and adapting it to have beliefs about something else. That's the way I thought about Dempster-shafer. And I'm interested in situations where you have bets which define less than a probability distribution. But even those extensions of probability theory I think of as occupying a very small space in our world of uncertainty. So the fact that you have certain situations to which these models don't apply or are useful is fine with me. That doesn't bother me.
But what would you do if you don't know what is the frame of discernment, so to speak? What would
Then you have nothing to discern.
you might have partial ideas of what that is, but not exactly. I don't know. I find this. I don't know if there's an answer to that. It's just that especially with like rare events that happen, and in retrospect, we did not even see that coming. That kind of, it's the same story that, you know, looking into the future, we still don't know what could possibly be imagined, and not to mention putting down a number on that.
To my knowledge, it seems that some people are interested in trying to formalize the notion of natural statistical model. But of course, you still have to bring on board some knowledge of the parameter or something. But once you know what the parameter is supposed to represent, then you know the state space.
So you're formalizing the notion of a natural statistical model?
Yes. The idea is that suppose that you have, for example, suppose you have a normal distribution and you have your mu and sigma. Some statistical model of the mu, like as a function of mu and sigma, and that gives you a parameter space. Some statistical model of those forms are natural, whereas if you just take a random function of mu and sigma, say mu plus sigma divided by 2, and get a parameter space, and people think that's just unnatural, and you can't just do inference on that. So
you're speaking of the kind of natural in the sense of perhaps Peter McCullough and his.
Yes.
Okay.
What's his sense of natural?
What is the probability model? What is the statistical model? Do you remember that he has a paper called?
I'm not sure if I remember. I'm not sure whether I've forgotten or didn't know. What is its concept?
So Peter McCullough had this paper called "What is a Statistical Model?" And it was a very difficult paper, but I think I actually like it. He was trying to say what it means to have a statistical model, and there is a sense of what is a natural. Some parameters are natural, some are not.
I think McCullough was Kerry's advisor, so he should know. He can explain this to us.
I don't know if I can explain it to you, but it has to do with natural transformations.
That's true.
Yeah. I couldn't recall, regurgitate it at this point. But, so you're trying to think, okay, but now at least I know what you mean by natural. But what are you trying to do?
Oh no, I was just reacting to, not reacting, like this may not be related to what Ruobin was saying, but I feel like in terms of the ignorance of models, for example, if we are ignorant of the state space or parameter space, then it seems like we may have some traction on that problem. If we want to say, even if we don't know where our models are, but probably we can put some naturalness constraint, and then say, oh, we're not entirely ignorant, but of course we have to put in some information in the first place, and then try to see how to cook up a model from that information.
Because that's all. I mean, one of the elements of that is that a model should be unaffected by if you measure temperature in Celsius or Fahrenheit, things like that. So certain transformations of the data should leave the model invariant, or should preserve the structure of the model. And so that. So if you don't know, you may not know what it is you're observing, but you might have an idea about its structure. Is that possible?
It's very Keynesian, I think.
Ask you some technical points
Yeah.
about the talk. So first I was wondering, for the first part of the talk, does it apply to infinite dimensional data, or does it only apply to finite dimensional?
Does it apply? I have not tried to take k to infinity.
Okay. Yeah, I was just wondering whether or not it's the same thing.
I've not thought about it. But what does it mean to say that I have a multinomial I'm taking k to infinity? Maybe that becomes a process of some sort, or a continuous distribution. I've not thought about it. No.
I see.
Yeah.
Okay. Yeah, I was just wondering. Sometimes you can it seems like you can do the same thing in the infinite dimensional case, but sometimes
Yeah, I think our Dempster would always argue otherwise and say everything's about multinomial, because you always truncate the real line into like just the a finite numbers of pieces and look at data kind of in bins. That's how he come to motivate that. Instead of thinking about taking k to infinity, but to take k from infinity to something that's rather small. So I've not thought about it. I don't know if these things would hold. I don't know what is a simplex infinity. That's not. The model being, I have this Q of x that, which, this would be like a three-dimensional multinomial. I'm drawing random sets that look like these. But what if it's a simplex instead of three?
You're observing
I'm observing a vector of 3 of counts.
1, 1?
Yeah.
I would think that one motivation might be you don't want to put an upper bound on the number of observations you're going to have.
Yeah, so I don't know if this would work, but you could do the infinite simplex, but when you label the classes, you would run additions. So usually what you would do is you would rank the observations in decreasing order or something like that. So this would be in species sampling, for example. You don't want to put an upper bound on species. You might observe an animal that's of the species you haven't observed before. So this is what you get is a random partition instead of what amounts here to a labeled partition.
So one thing that I can say is that because in multinomial inference, and Peter Wally again wrote this imprecise derivative model, which was very famous. Everybody would know about that one for multinomial inference. One thing there are few criteria that ideally a multinomial model should satisfy. Invariance. If you swap the labels, your things should stay invariance. If you look at the margins, so any subset of those multinomial counts, your inference should still be the same. And this does satisfy that because of so if I were to project this k-dimensional thing to a sub-k-dimensional thing, it preserves the same structure. So at least it has that. There are, again, so that's kind of getting to your question about thinking about k being embedded in a larger k or stuff like that.
You can just always take the projection.
So I think our Dempster's idea here, going back to the 1960s, was that you solve the multinomial, you solve this upper and lower probability problem with the multinomial, and then you solve it for continuous models by taking, as you were saying, a very large number of categories and then conditioning on the restriction imposed by that continuous model. So you would get a result, you would get upper and lower probabilities from observing, if your model was that something is, you were sampling from a normal distribution with unknown mean and variance, if you discretize that, you get something that's multinomial, but not all the multinomial probabilities are allowed. That
right.
Normal model is
right.
restricting which multinomial probabilities are allowed. So you do the theoretical analysis allowing any multinomial probabilities, and then you condition on the ones that are by that normal model. And that way, by solving the multinomial, in principle, you've solved everything. In principle, it's only a computational problem. As Ruobin says, the ambition there is not to go to infinity. The ambition is to recognize the finite nature of these supposedly infinite models, which are only idealizations, because the reality is really finite.
Yeah. Couldn't put that better. It's just that the computation is the only problem that has been the problem that deferred all of this for 60 years and counting. So I don't know. One could argue, it's not. Yeah, right.
There's got to be a trick.
Yeah, there's got to be a trick. I mean, the reason why I wrote this is because I didn't have to worry about computation. This is so our Dempster had a multinomial model a while ago. He's still thinking about how to do a Gibbs. I told him his thinking doesn't work. I didn't care for that one because this doesn't require that, which is why it's nice. But if we rely on having to come up with smart and cute models that didn't call for computation, that's not sustainable, right? So.
That's good.
Thank you very much.